Here is a combined summary of the two pages. Weyl fermions in topological metals exhibit spin momentum locking, a property resulting from the Berry curvature monopole nature of Weyl nodes. This leads to current-induced spin accumulation, which is maximized when the Fermi energy coincides with one of the nodes in a pair and reaches the same value as for an isolated node. However, in bulk Weyl semimetals, nodes must occur in pairs of opposite chirality, cancelling out the effect. Chiral semimetals, where nodes of opposite chirality occur at different energies due to broken mirror symmetry, avoid this cancellation. The authors develop a theory of current-induced spin accumulation in chiral topological semimetals using a toy model of a pair of opposite chirality Weyl nodes. They derive a set of coupled spin-charge diffusion equations, describing the intertwined transport of non-equilibrium spin and charge densities. The equations are obtained using the standard diagrammatic perturbation theory for the charge and spin density response, taking into account impurity scattering through the self-consistent Born approximation, SCBA, and ladder vertex corrections. The impurity averaged SCBA retarded Green's functions are expanded in the basis of a unit matrix and three Pauli matrices, and the density response function is evaluated using SCBA plus ladder vertex corrections. The transport equations are derived from the retarded density matrix response function, which is evaluated using the same approximation. The authors find that the spin accumulation in response to a charge current in chiral semimetals has a non-trivial non-monotonic dependence on the Fermi energy. The maximum spin accumulation is achieved when the Fermi energy coincides with the location of one of the nodes and decays away from this value. A closely related magnetoresistance effect is also demonstrated, where spin injection from a ferromagnetic contact leads to an extra contribution to the voltage drop, depending on the orientation of the magnetization of the ferromagnetic contact relative to the current. The theory is based on a simple toy model, but the qualitative effects should not depend significantly on details. The results are smooth functions of the Fermi energy, and the approximation used is at least qualitatively correct for any value of the Fermi energy. Here is a combined summary of pages 3 and 4 of the research paper. The authors investigate the spin-charge coupling physics in a chiral topological semimetal, focusing on the long-wavelength low-frequency response. They derive an expression for the susceptibility chi-ab, q, omega, in terms of the Fermi-Dirac distribution function and the inverse diffusion propagator, diffusion, d. The diffusion is evaluated at small omega and q, yielding a 2x2 matrix with entries that describe the coupling between the charge and longitudinal component of the spin. The authors highlight the significance of spin non-conservation due to spin momentum locking, which leads to a non-trivial coefficient in the inverse diffusion matrix. The authors then derive the coupled spin-charge transport equations, which are valid on time and length scales longer than the mean free time tau and mean free path L. They solve these equations in the steady state, assuming transport in the x direction, and obtain a new length scale LCs that characterizes the strength of the spin-charge coupling. The authors consider a semi-infinite sample with a ferromagnetic electrode at x equals 0, injecting a spin-polarized current into the chiral semimetal. They solve the equation for the spin density Sx, x, and find that it consists of an intrinsic spin polarization of the charge current and an extra spin density injected from the ferromagnetic electrode. The authors then calculate the voltage response to the injected current and find that it consists of an ohmic contribution and a non-ohmic contribution with a non-trivial scale dependence. The ratio of the non-ohmic and ohmic contributions, RO, is used to characterize the strength of the magnetoresistance effect. The authors highlight the non-monotonic dependence of RO on the Fermi energy, which vanishes at charge neutrality and far away from the Weyl nodes, and reaches a maximum magnitude when the Fermi energy coincides with the location of one of the nodes. The authors provide numerical results for the bulk current-induced spin accumulation and magnetoresistance as a function of the Fermi energy, demonstrating the non-monotonic behavior. They conclude that their results, including the expressions for the current-induced spin polarization and the magnetoresistance, are the main findings of their paper. The theory of current-induced spin accumulation and magnetoresistance in chiral semimetals is developed, where Weyl nodes of opposite topological charge occur at different energies due to broken inversion and mirror symmetries. The current-induced spin accumulation is maximized when the Fermi energy coincides with the location of one of the nodes, while vanishing both at charge neutrality and when the Fermi energy is far away from the nodes. The maximal spin accumulation achieved in this case is identical to that for an isolated Weyl node, which can only be realized as a surface state of a 4D quantum Hall insulator. A unique magnetoresistance effect is demonstrated, closely related to the current-induced spin accumulation, where a non-equilibrium spin density, injected from a spin-polarized electrode, leads to an extra contribution to the electrical conductivity. The sign of this effect depends on the relative orientation of the spin polarization of the electrode and the current in a way that distinguishes it from most other magnetoresistance mechanisms. The magnitude of this effect is also a non-monotonic function of the Fermi energy, reaching maximum when the Fermi energy coincides with the location of one of the Weyl nodes. The diffusion propagator is calculated using the self-consistent Born approximation (SCBA) equation for the impurity self-energy. The retarded Green's function and the wave functions are used to evaluate the momentum integrals. The matrix elements of the diffusion propagator are obtained, and the results are expanded to first order in ODE and up to second order in QL. The expressions may also be used in their original form to study diffusive ballistic crossover phenomena when ODE and QL may not be assumed to be small. The theory is applicable to thin films of currently known chiral semimetals, such as CoC and RHSI, although many details will certainly be different due to a more complex electronic structure of these materials. The results are expected to be observable in experiments, and the details will be investigated in future work. The research paper discusses the concept of topological materials, specifically focusing on the topological properties of magnetic topological insulators. The authors provide a comprehensive review of the current understanding of topological materials, citing various studies that have contributed to the field. The paper begins by introducing the concept of topological materials, which are materials that exhibit non-trivial topological properties. The authors highlight the importance of topological materials in the context of condensed matter physics, citing their potential applications in quantum computing and spintronics. The authors then delve into the specifics of magnetic topological insulators, which are a class of topological materials that exhibit both topological and magnetic properties. They discuss the theoretical framework for understanding these materials, citing studies that have developed models for describing their behavior. The paper also reviews experimental studies that have successfully grown and characterized magnetic topological insulators. The authors highlight the challenges associated with growing these materials, which require precise control over the growth conditions to achieve the desired topological properties. The authors also discuss the theoretical predictions for the topological properties of magnetic topological insulators, citing studies that have predicted the existence of topological states in these materials. They also review experimental studies that have observed these topological states, including the observation of quantum anomalous Hall effects and topological magnetoelectric effects. The paper concludes by highlighting the potential applications of magnetic topological insulators, including their use in quantum computing and spintronics. The authors also discuss the challenges associated with scaling up the growth of these materials and the need for further research to fully understand their properties. Throughout the paper, the authors provide a comprehensive review of the current state of research in magnetic topological insulators, citing numerous studies that have contributed to the field. They also highlight the challenges and opportunities associated with these materials, providing a roadmap for future research in this area.